Hello, hello, Linear Algebra Bros. We're going to discuss a theorem in this video, as well as look at some examples relating to it. So let's get started. Let S equal a set of what assumes to be R vectors. The theorem says if we form all the possible linear combinations of these vectors, then the set for which they're contained in is a subspace of V. And they want us to label it as W. I'd like to give you the set notation version of this subspace W. It's going to be the set of all linear combinations of W1 through WR. Let's write that as K1 W1 plus K2 W2 plus dot 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 KR WR. So that's what our objects look like. And I do want to put a little condition on our K1 through KR fellows in there. Each one of those K sub i's is a coefficient, aka scalar, and those will come from the set of real numbers. So I think we're probably good to say that K sub I is an element of the set of real numbers. So the set of all linear combinations such that each coefficient is a real number. I'm going to do my best to give you a little visual of what this theorem is speaking to. Let's say that this is my representation of a subspace, not a subspace, a vector space V. And let's assume that there were three vectors for the set S, W1, W2, yeah, you know what, I'll go for broke here, W1 through WR. Alright, so if we look at all those vectors that come from the set S, and if we start mixing them all together, think about what you get when you mix, two or more vectors together. You get another vector, don't you? So if we start mixing around, W1 through WR, and if we generate all of the possible mixtures of these vectors that we could make, then the set containing all those mixtures would be a subspace of W. I'm sorry, a subspace of V. So I'm going to represent the set of all mixtures of W1 through WR, this little green blob here. This is what they're referring to as the set W. And according to this theorem, this right here is a subspace of V. Alright, so it satisfies all 10 vector space axioms using the rule for addition and scalar multiplication on V. Now, this set W has a special name. The set is called the subspace of V that is spanned by the vectors from S. And the vectors that are generating the subspace are said to span the subspace W. And basically, they're kind of like subspace generators. They generate all of the vectors within W. And there's some notation that gets paired along with this. We could say that this subspace W is equal to span, and write the set of vectors in set notation along with that, or simply W equals span parentheses S, kind of like function notation or determinant notation there. You know what, I think I'll cut the video off here and do a separate video for examples of spanning sets. Alright, so let me know if you have any questions about this one. Otherwise, I'll see you in the next one.